Continuing beyond the previous video, in this video, we're going to talk about pandas, and this is part 2 of the pandas tutorial. If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started. Now there is another important method which is very popular, which is called value counts. Value counts essentially tells you the frequency of each category present in a column. So for DataFrame 1, we saw site and we just manually counted that A is appearing twice and C is appearing twice. It is not going to be practical with a few thousand rows, right? So you can use value counts there. It will tell you for each category what's the frequency. So if I run this, you see A is present twice, C is present twice, and B is present once. It shows it in the descending order by default. And if you want to convert it to percentages, you can use a parameter here, which is called normalize. When we put it as true, it is going to give us the percentage distribution of the A, B, C categories. So 40% A, 40% C, and 20% B. Right now in fractions, we can multiply it with 100 to convert it to percentage. Now in any data frame that we work on, one of the concerns that we always have to check is, do we have missing data in the data frame? And we have these kind of methods like isnull or notnull to check for it. Notnull essentially is exactly opposite of isnull. Isnull is going to return a true when it encounters a missing value, and otherwise it's a false. Notnull is opposite. Notnull is going to return a true when the value is present and false when the value is missing. So let's just take this original data frame. Original data frame didn't have missing values actually. We know this. And if I check anything like isnull, notnull, what is it going to give us the output? So isnull is a Boolean function. It's going to return a true wherever you have missing values. If you don't have missing values anywhere, it's going to return false throughout. Notnull, on the other hand, for the same data frame is going to return true throughout, because notnull is checking the presence of a value. Value is not null, it's a true, right? And if you do isnull.sum, it's supposed to return the sum of missing values by each feature. Let's run this. So see, the first output is a collection of all Booleans where everything is false. Why? Because we don't have any missing value. Second is a collection of all true values because it's a check on non-null. And we know that this data frame has no missing values, so it's going to say it's true throughout. And for each column, if we count the missing values, it says we don't have any, right? So let's introduce some missing values to be able to see these functions in action a little better. I'm making a copy of the original data frame, and I'm using an attribute called loc, which essentially is a location-based indexing. I'll be talking about it in some time, but for the time being, just understand that it requires inputs related to rows and columns. So we've chosen the row with index 4 and row with index 6 and column 1 and column 2. Let me show this to you in the original data frame. So row with index 4 is this row, as you can see, and row with index 6 is this row, as you can see. And we've taken column 1 and column 2. So essentially, we are referring to this value 5, this value E, this value 7, and this value G here. And what am I doing? I'm converting these 4 values to np.nan. Essentially, we are introducing missing values through this. So that's what this code intends to do. Now you'll see an output which will have some nans. Nan stands for not a number. So these are missing values now. Earlier, we had some values here at these places. Now those have been replaced with nan. Now we have missing values in a data frame called df with null. And let's see if we run that isnull, not null, or isnull.sum, what the output would be. So what do we expect for isnull? It should have true at these places because it is checking for the presence of null, right? So these 4 places, it should show a true. Not null should show a false here because these are the only 4 places where it does not find anything. Everywhere else, it finds something, so it will write it true. And isnull.sum should show a count of 2 for column 1 and column 2 because these 2 columns now have missing value. So let me run this and you'll get an idea. Places where it has a true, these are the places where we have missing values. That's isnull, right? We have put a print with a space here just to separate this output. If I don't write this, all these will be kind of merging. So this keeps the output somewhat neater. And if you see, column 1, column 2 have 2 missing values each. Similarly, for not null, as you can see here, the false values appear here because these are the only places where you have something other than not null. Likewise, let's now talk about this loc and iloc. I kind of use that to just introduce missing values, but I should also explain that to you. So let me just bring the original data frame here, as you can see. And let's say I do iloc when I pass the sequence of rows from 1 to 2. So when I write 1:3, it is going to count only 1 and 2. The upper value is not inclusive. And similarly, I write 1 3 for columns, it's going to take the first and the second column. So what are we saying? We're referring to index 1 and index 2. These two rows, index 1 and index 2 for the row selection. And we are referring to index 1 to index 2 for columns. Essentially, we are referring to these values B, C, and list must, right? Let's see what we get when we run this. See, it says the same thing output. So it's kind of a subset of the data that we've obtained based on selection of a specific rows and columns, right? In a large data, you may be asked to give information about certain rows, certain specific features, and you can do iloc there. Likewise, if I choose 4, 6, so now if you see, there's a difference. Here, the values that we gave were in sequence. This is called slicing. So we said 1, 2, 3. Of course, 3 is not counted, so 1 and 2 were obvious. But when we write 4, 6, it's not going to include 5 in between. It's only going to select the row with index 4 and row with index 6. Similarly, it's going to take the first column, which has index 0, and the column with index 2, which is the third column. If you're not very clear on the basic indexing here, you may refer to the earlier videos on NumPy arrays, and that will come handy for this piece. So we are referring to specific indices for rows and specific columns. And let's just, before we even print, guess the output. So row index 4 is this, and row index 6 is this. So we have 5E of 7G length. This is the piece. But we have not selected every column. We have selected only column with index 0 and column with index 3. So what we should get as an output will be 5 of 7 length. Nothing from this would come because index 1 is not presenting it. As you see, 5 of 7 length. That's the way we've selected. Just like we have iloc, iloc essentially works by the indexing. Loc works by the labels. So what is the difference between an index and a label? So far, when we referred to the column, we passed 0 and 2. It was going by the index 0, 1, and 2. But if we are doing loc, we'll have to give the exact name. Note in case of rows, it does not matter right now because our rows are not carrying any separate names. They only have those values starting from 0 to 6. So that's the reason for row, we don't have to worry about it. But for columns, because we're using loc, we have to give the exact name. Also observe that for loc and iloc, we don't use parentheses. We are using square brackets. That's a syntax specific thing. Let's run this. We get the output. Now, there are times when you're working with the data and you may have to change the data type. Let's say we look at the data frame 1, the one we created using an array earlier, and we want to change the age to float. So what is a float? Float would be the values which would contain decimals. So this right now is an integer, but we want to convert it to a float. So we can do using as type. This is called typecasting. We are converting it to a float and we can print the data. If you want to roll it back once again from, let's say, the float to an integer, we can always do that. If you're worrying about this 64 and 32, this has to do with the bits of information, and this would define the range of values that a variable can attain. But that's not so important for us right now, so we'll simply just run this. Observe the change here. So the values originally appeared without any decimal. We don't have decimal values actually, so it just added a 0.0 here to convert it to a float. But when we rolled it back to an integer, it again lost the same decimal representation. Can we convert a numerical value, which is, let's say, the same age? And right now, after executing this line, it would be an integer. Can we convert this to an object type, which is something like a string? Let's see. It doesn't appear to be any different compared to this, right? But if we check the data type of this variable now, it'll show O as an object. See, it says it's an object type variable. Can we convert this object type variable back to integer? Let's give it a try. So we are taking the variable called age. We are saying the same age variable we want to typecast to integer again. Last, we converted it to object. If you run this, it converts it back to integer. How do we know? We can check the data type again, and now it says integer. But can we do this for just about any feature? Let's say we have a feature called site, which has information like ABC. Can we typecast it to integer? This would result into an error because the values present in this column are not numerical in nature. These values, even though we converted them to object, still you had a 25. When you try to roll back the data type, that was feasible. But for A, it would not come up with the ASCII mapping and things like that, and it gives an error. That's the thing. So now let's talk about filtering the data. When we're working with data frames, at times we want to obtain specific filters on the data based on certain conditions. For example, somebody might ask you that, can you get me only those observations which have an age greater than or equal to 25? So you have to apply that filter. How do we apply filters? So it's data frame. Within a square bracket, we need to write the name of the feature on which we want to apply the condition and the specific condition. So we are saying greater than or equal to 25. There could be multiple conditions. We use parentheses and put and or operators to do that. But We'll not make it complex right now for the first timers. Let's keep it simple. We're just filtering this data based on the variable called age. This is the data frame, which has a column called age, and we're only choosing those values which are greater than or equal to 25. We're calling it as df sub. So if you see, it has filtered the observations which belong to age group of 25 and 27. If I show you the original df1, it of course had more observations like this, right? So there are values like 20, 23, and 23 one more time. These have not been selected because we wanted to specifically obtain values which are greater than or equal to 25. We can select specific columns as well from the data. So let's say we want to select only 2 columns. Now, if you're selecting just 1 column, you can use just 1 pair of square brackets. But if you're selecting 2 or more columns, you have to use 2 square brackets. df1, and we are only selecting employee ID and age. We are not selecting site. So we can do it, let's say df sub column. This is the name we've given, and you can see how it is. So it selected the employee ID and age. Lock and iloc we've already talked about, but we can do filtering based on lock and iloc as well. For example, we are saying that we want to filter those rows where the age is greater than 25. And for those people, we want to only display the employee ID. So if you see, we're using a combination of lock and a condition. Age will be greater than 25, but we don't want anything else for these people. We only want to figure out their employee ID. This is a filtered data frame. It'll only return the employee ID. Notice this time we did not put it as greater than or equal to, and in our data, there's only one value that's strictly greater than 25, which is 27. That's why it returned only that employee ID. We can also filter the data based on the conditions associated with missing values. For example, you may want to look at the rows which are incomplete, or you may want to only look at the rows which are complete. How do we do that? So the data frame where we introduce those 2 null values, if you remember, let me just print that here for you quickly, df with null. So this is the data frame where we introduce 4 missing values in 2 columns. We're referring to that data frame, and within that data frame, we are doing isnull.sum, but there's a change. Inside the sum, we are passing access as 1. Access is equal to 1 essentially refers to the rows which have missing values. So we are saying we only want those rows which have a count of missing values greater than 0, which means they have some missing values. So let's see what are the rows that it prints. It should print the row index 4 and row index 6, and it does that. Okay, so this is kind of a condition that we introduce. If we want to simply print the rows which do not contain any missing value, we have a ready method here, which is drop NA. And we can use drop NA, access is equal to 0. This will print the rows which have no missing value. You may be wondering why we are using access is equal to 1 here and access is equal to 0 here. So generally, 0 refers to the row and 1 refers to the column. But why did we then use access is equal to 1 here? So a row is made up of columns, right? So we are saying when we are doing a total of it, how are we going to do the total? For column 1, do we have a NaN? For column 2, do we have a NaN? For column 3, do we have a NaN? That's how we check it. That's why we had put an access 1 here. But here, we can straight away refer to the rows because this function is smart enough to do that for us. Similarly, if you want to select the columns which have missing values, take df with null dot columns. If you remember, dot columns was essentially the list of feature names. And what we are saying is that if any feature has any missing value, so this is dot any is also a method, it will go through the columns. If it encounters that the column has any missing value, which would mean 1 or more, it would filter that column and show it to us. Let's just run this. It's showing those columns to us which had missing values. The last column in our data frame, if you remember, had no missing value. That's why it didn't display. And similarly, if you want to display only the columns which are complete, which have no missing values, you can do drop NA, and this time access is equal to 1. That's how let's see what happens. It's giving us the information that column 1 and column 2 have 28.5% missing values, and column 3 has no missing value. Why is this able to calculate the percentage? Remember, this isNull is just a collection of true and false values. So true is typically considered 1 and false is considered 0. So when you take an average, it'll add up all the ones and divide it by the total. Since these 2 columns, column 1 and column 2, had 2 missing values each, and these had a total of 7 rows. So 2 by 7 is what it's giving us, essentially.